All right, well, let's get into some application problems. So if you've noticed in our class, whenever we dive deep into a function type, we also have applications of those functions. Like we had linear functions, so we had linear applications. We had quadratic functions, and we had quadratic function applications. Now we're going to have applications in exponential and log equations as well. All right, so let's look at number 6 and see how we can use what we've learned to answer these questions. It says a couple invests $8,000 in a bond fund. The expected yield is 4.5% and the earnings are reinvested monthly. So that tells us about some compounding. All right, this is our compounding interest formula to write a model representing the amount in the account after T years. The value R is the interest rate, and N is the number of times the interest is compounded per year. All right, so note that it says we want to represent our ending amount, so that's like our Y value, after T years. This is like our X value. So we're trying to find A of T here. Well, let's see what we're given in the problem. Do we know P? Yeah, we do. P is 8,000. Do we know N? Well, how many times are we compounding? It's monthly, so N is 12. Do we know R? Yeah, 4.5%, so R is 0.045. Okay, now we have everything we need to write our equation. So our function, ending amount of T, is 8,000. 1 plus 0.045 divided by 12 times 12t. This is the function where you plug in t in years and you get the ending amount. All right, so next question, it says determine how long it will take the initial investment to double, round to 1 decimal place. All right, so with these problems, you really have to read carefully. What is this question even asking for? Is it asking for our ending amount? How long? This means that we need to find the time. So we're solving for t. And then how long will it take the initial investment to double? Well, this tells us our ending amount, and it's 2 times our initial amount. So hopefully that makes sense. We're trying to find the time it takes our ending amount to be 2 times what we started with. Okay, so we're just going to plug that in. All right, so our A is going to be 2 times P, so 2 times 8,000. We got our 8,000, 1 plus 0.045 over 12 raised to the 12 times t. So the only variable here should be our time t. So how are we going to solve for t? What do we notice about its location? Well, the location of t is in the exponent. Well, what does that mean when our variable is in the exponent? That means we have an exponential function here. And so we have to remember, how do we go about solving exponential functions? Well, we need to get the exponential part by itself. All right, so that's our first step. I'll write that down. Get exponential by itself. And so the way we're going to do that is dividing both sides by 8,000. So I'll show all my steps. Okay, 8,000s are going to cancel, so we have 2 equals 1 plus 0.045 over 12 raised to the 12t. All right, what's our next step? How do we solve an exponential? Well, Do we want to try to get the same base on both sides? This base looks pretty complicated to make it look like that over here. Maybe we just want to take a log of both sides. And it doesn't matter which log. I usually like to use the natural log. So I am going to take the natural log of both sides. So all of that is inside of my natural log. All right, again, we need to think about the goal. What is the goal here? We're trying to find time. We're trying to solve for time. Now it is inside of a log. It's also the exponential of this exponential function. But the reason why we wanted to use logs is so we could use our log properties, especially the one that says if you have an exponent inside of our log, we can bring it to the front and make it a coefficient. And so this is going to help us out so much. So we have 12 times this interesting log. But that's good because our t is now outside. We can solve for that. We can divide by this natural log over here, and we can divide by the 12. So this is our t. All right, let's also talk about putting this in the calculator because the order and parentheses all matters, and things are very difficult when multiple things are happening in the denominator. So my suggestion is to do the denominator first. All right, so I am going to do the natural log of 1 plus, and in parentheses, point, oh, I messed that up a long time ago. There should be a 0 in here. 0.45. Sorry about that. All right, natural log of 1 plus 0.045. Whoops, I'm just going to start over. Natural log of 1 plus parentheses 0.045 divided by 12. Close both of these parentheses. All right, I could have also multiplied by 12 in that step. So then I multiply by 12. So this is what my denominator is. I'm not going to do anything with it. I am just going to go straight to the natural log of 2 and divide by second answer to give me my answer. So I have natural log of 2 divided by my answer from above, and so I get 15.4 as my time. So t is about 15.4. Time in this case is in years. All right, so we're going to be using this process a lot.